All right, so in this video, we're going to talk about the conservation of power, sort of the concept that I mentioned in the last video. So let's write out those two expressions again. We've got V1 over N1 equals V2 over N2, which basically becomes V2 over V1 equals N2 over N1, and that's equal to I1 over I2, right? And so from this expression, we can derive that V2 over V1 is equal to I1 over I2, right? We're just taking these two that I just said are equivalent, setting them equal to each other. And so if I multiply, and do a little bit of cross multiplication here and rearrange this, I can write that I1 times V1 is equal to I2 times V2. And that right there is conservation of power. Basically, is telling me that my product of my input current and voltage, which are these two quantities here, is equal to the product of my output voltage and current, which is these two quantities here. And so, of course, we could just say that I1 times V1 is equal to the input power, P in, and we can say that I2 times V2 is equal to the output power, P out, and therefore we can just say that P in is equal to P out. That is the conservation of power. And that's basically just showing that we can't both step up the voltage and the current, right? In order for these to stay equivalent, right? If I have a fixed I1 and V1, in order for this term to stay equal, if I raise the voltage, I have to drop the current. If I raise the current, I have to drop the voltage. I cannot boost both of these and have it stay equivalent to this input power. That just makes no sense, right? And so let's just see what that might look like. Say I've got a source here driving. I guess this is pretty similar to what I already did in the previous slide. Drive a resistive load, RL. And let's just say that this is 2 times the sine 2 pi ft. And let's say this is a 2-to-1 transformer, okay? And I'll call this I1, call this I2, and then we'll call the voltage across the secondary or the load V2. We'll call this one V1. Okay, so I want to determine the currents flowing here and the voltages in this circuit. Let's just say that's what I'm after here. So first and foremost, you know that this is a 2-to-1 transformer, and so you know that the voltage is going to be stepped down. Maybe you're not super confident on the polarity of the voltage yet. I guess I neglected to mention that, but if you see here, the positive polarity of the voltage is always given at the dotted terminal. And so that's why they kind of show here that for the dots on the same end, you get positive polarity on the dot on the primary side and on the negative side. If we flip the dot, now you get positive polarity on the dot and it flips this voltage, right? Because the positive voltage polarity is always where the dot is. You can see that from this figure. So in this example, positive voltage polarity is going to be up here, so I've drawn this correctly. And I know it's a 2-to-1 transformer, so I can just say that V2 is going to basically be V1 divided by 2 is equal to sine of 2 pi ft, right? And my current, I2, is obviously the sine of 2 pi ft divided by RL. And so what is I1? Well, we know that we stepped the current down, going this way, the current has to be stepped down because the voltage is stepped up, right? From this side, the ratio is 1 to 2 going this way, so the current has to go 2 to 1. So whatever this current is, this current has to be half that value. So since we already know I2 is sine of 2 pi ft over RL, we know that I1 has to be the sine of 2 pi ft divided by 2 times RL. And that would be that for that problem. Okay, so that's conservation of power. Basically just tells us that if we step one quantity up, we have to step the other quantity down. And that's going to be a very important governing principle for these transformers as we solve these problems. So definitely keep this in your back pocket. All right, so I'm going to go ahead and end this video. In the next video, I think we're going to solve an example problem. Yes, we're going to solve an example problem using transformers. All right, so I'm going to end this video right here, and we'll see you in the next one.